Okay, so let's work a ballistics problem. All right, and so if you're not sure what that means, that ballistics is all about the trajectories and the physics of the bullets, okay, that sort of thing, um, or any kind of munitions that is projectile-like. So anyhow, what we've got here is we're going to fire a bullet out of a 38 caliber gun, and we're going to let it go. Into a block of ballistics gel, which is used to test bullets sometimes. And our bullet's going to go, it's going to go into the block, but it's going to pass all the way through the block. All right, and emerge on the other side. And of course, it's going to slow down while it's inside the block. And so we're going to go, the bullet's going to go from 300 meters per second down to about 150 meters per second. So it's going to get cut in half while it's traversing the gel, and the gel, of course, is feels a force from that bullet, okay, and it's going to end up moving. Now, our particular situation, we're going to allow the gel to move. All right, so we've got it on some kind of cart to frictionless carriage or something like that. So it's going to go, it's going to hit the gel, and then the gel is going to be moving. All right, and our task in this one is to figure out what is the speed of that gel. Okay, so let's get our sketch going on here. Okay, and so we're gonna have our before and after. So we're gonna have our bullet is here. Okay, it's got a velocity of 300. It's headed this way, and then we've got our gel here, and the velocity of the gel initially is 0. Okay. Now let's go ahead and get our mass on here. So the mass of the bullet is 9 milligrams. Okay. See there? Milligrams. Oh, sorry, that's not milligrams. That's just grams. My bad. Back that baby up. Okay. We're just going to say 9 grams. There we go. Okay, and then mass of the gel is 1.5 kilograms. Okay. All right, so there's before. And afterwards, okay, we're going to have a hole punched through our gel. And the final velocity of the gel, we don't know. That's what we're looking for, but we do know that when the bullet emerges, it's going 150. Okay, just like this. Boom. Okay, and yeah, there we go. There's our sketch. Okay, so let's get to it here. So we're going to say our initial momentum. It's our final momentum. So initially, all we have moving is the bullet. So we're going to have this mass of the bullet, VBI, the initial velocity of the bullet. And then that's going to turn into mass of the bullet, VB final for the bullet, plus the mass of the gel, VB, oops, not VB, VG final for the gel. Okay, just like that. Okay, now we're looking for VG. Okay, again, there's some algebra involved here. Work through it. Make sure you can do it quickly and easily. And once you do get through that, this is what you're going to get. Okay, we're going to end up here with, oh, now I got to do it in my head. So, yeah, there we go. MB over MG onto VB initial minus VB final. Okay, just like that. Okay, so let's throw some numbers in here. The mass of our bullet is very small, 0.009 kilograms. Mass of our gel is 1.5 kilograms. And our initial velocity for a bullet is 300. And then finally, we got 150 meters per second. Okay, and so those are going to cancel out. All we're going to be left with is the 150, okay, which makes sense because we're looking for a velocity. And so after we plug in our numbers here, what we end up getting is 0.9 meters per second. Okay, so the gel's going pretty slowly, okay, just like that. Okay, now this, we actually don't have enough information to do that. So I'm not sure what I was thinking. Actually, that one was a different question, I think. Copy paste shenanigans. Okay, so there we go. Boom, boom. So that would be considered a through and through type situation. Okay. Now, I want you to notice here, I mean, we don't really know anything about this situation, but you can see that the bullet lost half of its velocity, and the object that got hit at 0.9 meters per second, that's pretty slow. Okay, that's about like this. Okay, that's about 0.9 in 1 second, if I can get it all in one frame. Okay, about here. So go right there. So that's what we're talking about right there. So that's not very fast. Now, what if the gel was more than 1.5 kilograms? Okay, what if it was 15? Okay, see what's going to happen here. If it's 15, then this number down here becomes 15, and then this number becomes 0.09. Okay, sort of like that. So the more massive the block gets, the less we have for its final velocity that way. Okay, now it's going to be important in just a minute. So let's look at another scenario here. Okay, so in this one, okay, it's a little bit different. All right, in this experiment, they slowed the bullet down. Okay, and so the bullet initially is only going 100 meters per second. Okay, it's going to hit the gel, and that's still stationary. Okay, but because it's going slower, okay, it's not able to get all the way through the block of gel, and in this case, it gets embedded into the block of gel. So our afterwards system, we've got a sticky collision here with our bullet buried inside our gel there, and we have a combined bullet gel speed, and we don't know what that is. Okay, we don't know what that is, but take a look. What's the question actually asking about? It's actually asking about the force from the bullet. Okay, so now we're going to get to how much force does the bullet apply to the block of gel. Okay, all right, so let's think about what's happening with forces here. Okay, so we know we're gonna have some weight. We know we're gonna have a normal force here. Okay, and then there's the force of the bullet, just like this. Okay, now we're gonna ignore friction. Okay, and I'll show you when we get to the end. I'll kind of talk a little bit about what difference that might make in our situation. Okay, but we know we're going to have some acceleration this way. So if we look at a free body diagram here, then we're going to have the force from the bullet here, the weight, and the normal force there. And then, of course, we have got our acceleration this way. Okay, so since we're talking about forces, let's start there. Okay, and vertically, I'm just going to ignore vertical because we can see right away the normal force is going to equal the weight. We've done that 30 times. Okay, we got that. And this is a simple situation. So we're going to say here that sum of the x forces is max. Okay, so what do we have? We've got the force of the bullet. That's the only force we have horizontally. And then we're going to put ma just like that. Now, this is actually the mass of the gel. Okay, because the bullet is acting on the gel. So what we're interested in is what's happening to the gel. So we use the mass of the gel in that slot right there. Okay. So if we knew the acceleration, then we could work this thing out. Boom, and we'd be all done. Okay. How can we get the acceleration? Well, okay. We need to know, we're going to need to know, we know it's gone in 3.5 centimeters, right? Okay. And so the force is going to be applied that way. Okay. So we're going to roll with that. Okay. We're going to assume it takes it 3.5 centimeters to accelerate. So the bullet might actually penetrate slightly less, but the acceleration distance will be 3.5 centimeters. Okay. What I'm trying to get to is we're going to use Bumblebee. V final squared. It's V initial squared plus 2a delta x. Okay. Now the initial velocity for the gel is 0. Okay. And what I want to do is I want to find the acceleration. So algebraically, let's turn this around. And let's say we're going to have here Vf squared over 2 delta x. Okay, just like so. All right, and so now what we need is that velocity. Okay, aha! Now we can use momentum. Okay, so we're going to use some momentum here. P initial, P final. So we've got the mass of the bullet, the initial speed of the bullet, which is only 100 this time, and they're combined together in the end. So the mass of the bullet plus the gel, and then we're going to have VBG right there. Okay, and so we can see here that VBG is going to be VB initial. Okay, and it's going to be mass of the bullet over the combined mass, like so. Okay, and if we put in some numbers there, we've got 100 meters per second and 0.009 divided by 1.509 for the combined mass, just like that. And what we end up getting for that velocity there is 0.596. Okay, considerably slower than what we had before, but that makes sense, right? Because the bullet was going slower when it began, right? Okay, so that makes sense. And now what we're going to do is we're going to take that number and we're going to put it up above. Okay, so we can figure out the acceleration. Okay, so I'm going to have my 0.596 number. We're divided by 2 and 0.035 meters. Okay, this is meters per second in there. Okay, and what I'm going to get for my acceleration when I do that is I'm going to get 5.08. Okay, meters per second squared. All right, then I can plug that in up here. So I can finally now get the force of the bullet is going to be the mass of the bullet, which is not the bullet, the gel. The mass of the gel, which is 1.5 kilograms. And our acceleration is 5.08 meters per second squared, like so. And when we do that, we get this whopping force of 7.62 newtons. Okay? Okay, now, I don't know. I don't know if that number surprises you. Okay? I mean, that is pretty small. Okay? We could ramp up the velocity of the bullet and see what that does with our force. So if we ended up, say we go back to 300 meters per second, what that's going to do for us is it's going to triple this number. Okay. Triple that number because that's linear. And then, but when we plug that in up here, we're going to end up with 3 times 3 is 9, something that's 9 times as great. And so that means down here, we're going to have something that's 9 times as great. Okay. And so now we're talking about, 65-ish, 66 newtons. Okay. Which is still not a lot. That's like the weight of 6 kilograms, right? Okay. So this is a little bit hard to get your head around because we're used to thinking about, bullets and movies. Okay. And in a movie, someone gets shot, boom, like that. And they're like, whoa, they go flying back. Right. Okay. That's what happens all the time. But when you put numbers to it, you find out that the force is not actually very large. Okay. And it's like, okay, well, maybe did we screw up our calculation here somewhere? Well, maybe we did. Maybe we did. How could we make this more realistic? Well, we could make it more realistic by putting maybe the mass of a person in here. Okay. What if we put in 80 down here, an 80 kilogram person, which would make this 80.009. Okay. Well, what does that do? Well, that's not particularly helpful because that means your final speed is only 1.63 meters per second. Okay. And that means your final force turns out to be about, oh, I got that. That's the wrong number. Sorry about that. What I wrote was the acceleration. Our final speed is 0.0337 meters per second, which is a pretty small acceleration, and your force actually drops down to about 1.301. Okay. Now, that still assumes the same acceleration distance for the person. Okay. So if you had a person wearing some body armor and they got hit with this bullet, okay, they would sort of collapse a little bit. Their body would give some. And so we're assuming that you give that much and the bullet is stopped. Okay. Or alternately, the person's not wearing body armor. The bullet penetrates but stops inside their body. Okay. But we still have the same acceleration distance of 3.5 centimeters. Okay. Still not an impressive force. So what's the take-home message here? The take-home message here is that there's a couple of them. First and most important is Hollywood lies. Okay. That's, every time you see somebody get shot in the movies, that's not what it's like in reality. Okay. So there's going to be very little motion of the body as a whole, when this happens. Okay. And, so anyway, but there's should be no real disappointment there. The higher the velocity of the gun, of the bullet that emerges from the barrel, all right, the more probability of what's called through and through. So the bullet leaves the body. Then that puts us in the same scenario we had before. Okay. And you can see, we had really in our last problem where we went through the ballistic gel, we still ended up with a teeny tiny amount of motion there. And so if that was a person, there's not going to be a lot of momentum imparted to that person. And so they're still not going to fly back like that. Okay. So that's the first and foremost. Hollywood lies. Okay. And the second thing is it matters that Hollywood lies. I mean, it's fun to have a dramatic movie, but that's how people think. That's what people think happens when a person gets shot. So if you are someone who feels like you need a handgun on you to protect yourself against a bad guy, you need to realize there's a very good chance that even if you should have to shoot at them, and if you're lucky enough to hit them, which is those are two separate things, and it's a whole nother conversation, they're probably not going to stop. Okay. Unless you're packing around a Desert Eagle 50 caliber handgun, they're going to keep coming at you if they are determined. Okay. So what the bullet does, the way it stops a person, is through internal bleeding. Okay. When you have enough system damage, then you lose blood, and when you lose blood, your blood pressure drops. If your blood pressure drops a certain amount, then you will pass out. Okay, and at that point, the threat is obviously neutralized. Okay, but it's very hard to just stop somebody with a single shot. Okay, that's super rare. Okay, if you're some kind of great sniper or something like that, you could do it, but then you got to train like that. You got to keep training like that and all that kind of thing. But anyway, there are a few tactical schools of thought that teach for defensive handgun training. They teach shooting at the hip. Okay, and the idea there is if you do hit somebody in the hip bone, you break their hip bone, and then they can't walk. They're done. Okay, they certainly can't pursue you that way. So that's a different school of thought. And then one could argue, but that's a pretty specific target to try and hit when you're feeling threatened. Because when you feel threatened, your pulse goes up. And when your pulse goes up, your cognitive functions go down, as does your dexterity. Okay, so you have to train in very intense, emotionally difficult circumstances to be able to pull that off. So realistically, could you shoot somebody in the pelvis? I don't know, you could try, but just it's going to be a lower probability than just trying to hit their torso, and that's hard enough when you're terrified for your life. So anyway, there's a video I posted where they shoot it's a 5-gallon barrel of water, like you'd see for like a water cooler, this jug of water, and they put a bulletproof vest around it. It's pretty great, and they shoot it with different guns, and then they look at the water that comes shooting up at the top as sort of an indication of what's happening. And everything we've done here is consistent with the results that they get there. Okay, so you wouldn't want. If you were wearing body armor, you still wouldn't want to get shot. It would still hurt. It would hurt a lot. Okay, but anyway, the force involved in those impacts is not nearly as much as we're led to believe by Hollywood. Okay, well, anyway, there we go. I had a good time talking about it.